Howdy. So what we're doing today, we have kind of like 4 topics that we need to make little pit stops at. So we are going to talk about carbocation rearrangements, then making alcohols leave, then ethers, then epoxides. Ooh, spoilers. Then we are going to do a synthesis problem together and an extra talent problem. Today we are going to try to get through like 4 talent problems together, or like parts of 4 of them. So I'm going to be moving somewhat quickly. And also I'm trying out a lot of new things in this that I didn't do last year. So I swapped out a lot of the problems. So pacing, we're still working on. One kind of announcement thing, remember, so I set aside 13.5 hours for next week. The first email of signups has gone out to the students who have like scored lower on the exam and giving them first priority to sign up. The next email will go out with signups this evening, then one tomorrow morning, then one tomorrow afternoon. From the time you get that email, you have 12 hours before it's sent to another large group of people. So I would suggest when you get the email, sign up for a slot. There are 10-minute meeting slots. I'll be in Smith Campus Center. I need to get a sweater because it's freezing. Yeah, especially if I'm gonna be there 13 hours, like, you know. So if you need more time, if you're like, I really need 20 minutes, I did set in buffers. Like I think the minimum, if I was to do 10 minutes with everyone, was like 10 hours. I did 13 hours. So like there's time built in for more people to like meet a little bit longer if you need to. So sign up if you need to, but again, y'all are kind of crushing it. So that's coming out in the next couple days. Remember to do the evaluations. So far, y'all have been real funny on the evaluations. Like one of the comments I've thought about just over and over for the past like 12 hours. It was like something along the lines of like, lecture just isn't very interesting, but I don't know what Tim could do to make it interesting. So I guess I don't know what I want. And that was the whole comment. And I lived. I was like, this is shady in the best way, but also like work. Generally, y'all have been pretty sweet in the evaluation so far. About a quarter of you have done it. So keep peer pressuring your friends to fill out the review. I think that the biggest kind of negative, or not negative, the biggest like constructive feedback I've gotten is I go quickly, which, yeah, I kind of have to. And I try to do like a balance, but we're actually fairly split on the Monday versus the Friday help room hours. So if that's something that you care about, vote for that, however you want. Again, with the help room, we just have some constraints. Like all we are paid for is Jeremy and Matthew are paid for 90 minutes of section help time, and I'm paid for 3 hours. So, and then Tim wants to do an hour and a half, but he is not technically required. Like he could just be by appointment. And so trying to find a schedule that works for everyone with the help room is real tough. But I hear y'all, and I hear it's been a thing for many years now, people being frustrated that help room's only on Monday. If we had teaching staff of 15, we would have help room all over the weekend. But yeah, that's just what we're doing. Any kind of logistical questions before we jump in? By Wednesday. Yep. And remember, regrade request and active are due tonight. Ding dong. Okay, let's jump into the first topic. And now the first test is, how do you pronounce this word? Not carbocation. So recall from last time, we talked about as our carbon gets more substituted, it gets more stable. And that's because we have more hyperconjugation. Hyperconjugation is when a sigma bond just kind of leans over towards a positive charge and helps to stabilize it. So what is more stable than a tertiary carbocation? An allylic cation. So any cation that you could stabilize via resonance is automatically going to be better than a tertiary. But this is the general kind of thing that we're thinking about here with carbocations. Now, our key idea for this new kind of concept of carbocation rearrangement is if you can form a more stable molecule, you will. And so what we have is this basic idea of a carbocation rearrangement. So what type of carbocation do we have right here? Primary, secondary, or tertiary? Secondary, and it's next to what type of carbon is this? Tertiary. So if we have a secondary carbocation next to a tertiary carbon, our sigma CH, it's almost like hyperconjugation went too far. And it's just like, I'm going to help you. And then abandon my current carbon. So what we get is a hydride shift, 1,2 hydride shift. And now what carbocation do we have here in the product? Tertiary. So what we did was we went from a secondary to a tertiary carbocation. And in doing so, we made a more stable molecule. So again, the big idea, when we can make a more stable molecule, we will. Now, if we have a secondary carbocation adjacent to a quaternary carbon, so this carbon's attached to 4 things, then what we'll see is a methyl shift. So the whole methyl group will move over. And then again, we have a tertiary carbocation. So we're moving from secondary to tertiary carbocation, making a more stable molecule. Does this idea seem okay? Okay. So warning, whenever you make a carbocation, you need to look left and look right and ask, can anything rearrange? Because if you don't, it is like walking across Mass Ave without checking to see if that light is walk, is go. And this could be you on the exam if you don't check for rearrangements. You think you're going somewhere. You think, oh, I'm going to ace organic chemistry and check for rearrangements. Heard? Thank you. Okay, so what I've decided to do is this, I think that y'all can get. Like, this is a bit more straightforward, but the piece that has some rearrangements that are hard and that are weird. And I think it's going to be more helpful for y'all if we do the hard, weird ones together, okay? So these are the base cases. These are the main ones that you would be expected to just come up and kind of like pull out of the air. Whereas these next ones are going to be a little bit trickier, okay? So first, here we have what type of carbocation? Secondary, and it's next to a tertiary carbon. So what would you expect initially to happen? Yeah, we would expect a hydride shift, and we would expect to get something like moving this here, and then like hydrogen moves over here. That's not what happens. So what do you notice about our boxy boy? Strain. She wants to be 109.5, but is contained to 90. You know, she just doesn't fit. So what happens here is we are going to try to bust open this ring and not completely break the ring, but just expand it slightly so that we can get closer to those ideal bonds. So when our ring is kind of like too tight, it's something called ring strain. So one reason that we can do a rearrangement is to alleviate ring strain. So what's going to happen is our carbon-carbon bond here, the sigma bond, is going to do a shift. And we can just call this a 1,2 alkyl shift. So alkyl instead of methyl or hydride. Now, if we count our carbons, 1, 2, 3, 4, 5, we should form a 5-membered ring. And if I'd make it 1, 2, 3, 4, 5, well, carbon 1 needs to have a methyl on it. But where should our carbocation be? Who did we steal a bond from? Go ahead. What? 2. Yeah, 2 had its 4 bonds. She was happy. And then everything changed when, I was going to say the Fire Nation attacked, but when the rearrangement occurred. So when we did this, we took a bond away from 2. So 2 is what has the carbocation. Now 5 just went from like having a wife to having another wife. Like just, they have 4 bonds both times, so still neutral. So now, what kind of carbocation is this? Secondary, right? Okay. So, we went from secondary to secondary, but we alleviated the ring strain. That's why we did the shift. We made a more stable molecule. Now, we do have a secondary carbocation adjacent to a tertiary carbon still. So what can we do? A hydride shift. And so you go from this boy to this one. Whoa. And that's from moving this hydride over and from doing the alkyl shift. Yeah. it's kind of a thing of like, if you write it, it makes it more clear that you know what's going on. But if you don't write it and you do it correctly, we're not going to know. And yes. Okay, so let's look up another one. So this is from challenge problem 6, and she's kind of an intermediate. It's not the starting material. I think initially there's like some leaving group on it, and then the leaving group leaves. But what is going to happen is we are told that this is going to make a molecule. It looks like this, where we have a 5-membered ring and a 6-membered ring. Let's look at our rings as they currently exist here, because she's weird. So we have one ring that's like this. How many carbons is she? 6. And we have another ring that's here. How many carbons is she? 6. And then we have this. How many carbons is she? 8. So it's kind of like we have a big octagon. And then in that, we have a 6 and a 6. And we're like double counting carbons because they're part of multiple rings, right? But notably, we don't have this bridge over here in our product. So what we need to do is we need to do some sort of alkyl shift that gets rid of our bridge here and gets rid of our 6 and 6 and makes one a 6 and one a 5. So what kind of shift do you think that we are going to do? Like if I label these carbons, I'm just going to number. Oh, right, it's 6, 6, 7, 8, 9, 9 carbons. Then what bond between carbon 1 and carbon 1, what do you think is going to shift and help accomplish this goal? Yeah. So we could do a hydride shift. And if we did that, you're totally right. We would make a tertiary carbocation. Have we done anything with the ring? No. So that's the thing of that's what we would expect you to predict if we didn't give you a product. But if we're giving you a product, then trace more of like, where did the carbons go? Like, we know we need to move a carbon-carbon bond somewhere so that we do not have this bridge anymore. So where do you think that we should shift? Lachey? Yeah. So let's try it. And really, there's some symmetry in this molecule. And so like you could do several shifts and accomplish this ring structure. Let's try this 6-7 bond. If we do a shift up, then, oof, woof. I am going to try really quickly, like not at a speed that y'all should like try to copy because I also might do it wrong. I'm just going to try if I can draw this in a way that like looks. We're not going to do that. So what we're going to do instead is say, did we do anything to this 6-membered ring? Is this 6-membered ring still going to be intact? It is, right? But then this 6-membered ring, we're collapsing and making a 5-membered ring. So what 2 carbons are going to be these boundary carbons between the 6 and 5-membered ring? Because I traced the 6-membered ring and none of those bonds moved. Whereas the other one, a bond moved. So I don't necessarily know exactly that the other one's going to be a 5-carbon thing, but I do know that one of my 6-carbon rings stays the same. Do you buy that so far? Okay. So when we do that, when we shift it, what are our 2 boundary carbons between the ring going to be? The ones that are attached to both rings. 3 and 9. So let's just draw our like little structure. And let's just say this is 9, this is 3. And again, we're just using this as a tool to help us draw right now. Well, our 6-membered ring, we're still going to have 9 connected to what carbon? On our 6-membered ring? 7. Good. And then 7's connected to 7 connected to 8. And then 8's connected to 1, 1's connected to 2, and oh my gosh, we're back on to 3. So this is our 6-membered ring. Do we see the 6-membered ring? Yes, totally. So this 6-membered ring, none of the bonds break. We also know that this is going to shift up here. And so we know that this part of the ring is going to be attached at carbon 9 and carbon 3 in the original 6-member. So we call this 9 and 3. 9 is connected to 7 because we didn't break that bond. So I'm just calling this 7. 7's connected to 8. 8's connected to 1. 1's connected to 2. 2 is connected to 3. 3 is connected to 9. So that's our 6-member ring. That's what we are predicting. Like there are multiple ones that we could do, but we know that like either that bond or this bond, thank you, or this bond or this one goes up. And either, no matter how we do that, we are going to get a 5-membered ring and a 6-membered ring. So I'm just saying arbitrarily, let's do this one. And also, this is not something that we would expect you to predict out of nowhere. We have to give you a product if we're going to do weird things like this. Okay? So now 9 is connected to 3 and 7, but who else should she be connected to after the shift? 6. So we know this is 6. 6 is connected to 5, which is connected to 4 to 3. 5, 4, 3. This is also a problem that I would say at y'all's level right now is near impossible if you're not numbering carbons. So numbering carbons is going to become a more and more useful tool as things get more complicated, just to like give her a name. So so where did our carbocation go? Who did we rob a bond from? 7. So what we're going to do is we're going to end up with this carbocation here. So one thing that you might be asking is like, hold on, why did we do this? And the simple answer is because our product is like this. And then from here, you'll be able to kind of continue with the rest of the problem. And I think the actual product has like a acetate on it right here. And so you can be like, oh, okay, if we have a carbocation, we're adding an acetate, then what type of reaction does that? SN1, SN2, E1, E2? Okay, which of those reactions involves a carbocation? SN1, SN2, and then if we didn't make a double bond, we did a. If we did not make a double bond, we did a SN1. Good. Yes, Joe. Nope. 6 goes, so 6, its initial bonds are here. And then after we do our shift, 6 has replaced its 6-7 bond with a 6-9 bond. Yeah. So again, this is kind of tricky, but counting carbons, we will get there. Did I answer your question?
I think I'm just confused because I feel like we had 12 carbons before, we had 2 600 rings, now we have 5 and 6.
Okay, we had 2 6-membered rings, but 3 carbons were in both of them.
So we're just changing the number of carbons on the chip.
Yes, that's exactly it. All of these have 9 carbons. And it's kind of weird because we're giving you like crazy rings. Like y'all haven't done this stuff before. Lachey. Yeah. Or wait, no, Katie is the one that had a question. I thought you were raising your hand. Yeah, because I think it's really unreasonable for you to try to go from this to drawing it like in 3D. Like this is something that like I have trouble with. I have a chemistry degree from Harvard. So like, and like even this looks ugly. So what I think is fall back on the skills of like numbering, and like that will kind of like give you a 1-for-1. Yes, and then we'll go on. Then we would do a different numbering system. Then we would have 3, 9 as the boundary, but then 9 would be connected to 8 over here. And then we would just like renumber. Hypothetically. So there's technically an intricacy here that I don't want to get into. That's like we have hydrogens here. And so we could have these cis, or we could have them trans to each other. That's beyond what we care about. we've given you the structure, so you will know which one it is. And so you are just going to move one of them and say, hey, I make this. This, yeah. But we need to go on. I'm so sorry. So challenge problem 3. So challenge problem 3, you have these molecules, which I've written out in chairs for you. You're welcome. And we are going to make these products from them. So first of all, what's our leaving group over here? Our N2 group. Yes. And then we have an N2 over here. And then a rearrangement has occurred. So what do you see that has shifted from here to here? A methyl group, right? So she was over here, now she's over here. So one important note for this question is at the top of it, the instructions say, this carbocationic shift is observed to occur simultaneously with the departure of the leaving group. So this is happening so fast, we don't even form a carbocation first. Like we're just doing a rearrangement. And the rearrangements can get crazier and crazier. We're not going to go much crazier than like this. So do you remember Pavlovian conditioning? E2. Okay, we did okay. Anti-periplanar orientation of when we do an E2, we want our leaving group and our hydrogen to be in the same plane, anti to each other, right? And we said the reason is because we want our antibonding orbital to be lined up with sigma. So when we deprotonate, the electrons can just do a little Cupid shuffle over, right? So this idea is going to come back here. So if this is the leaving group, we know we need to break that bond. So let's draw the antibonding orbital. So if our sigma bond is here, then our sigma star bond is going to be like this. And what do you notice is right next to our sigma star bond? Immediately parallel to it. Our sigma carbon-carbon with that methyl. John, are you okay? You looked very overwhelmed and just like, which is a valid response to this. So what we see happen is our shift, getting this methyl group over to this carbon, is we have this sigma bond do a kind of rearrangement over here. And specifically, I would draw it from the bond to the carbon. And then we kick off our leaving group. So now let's draw what we form when we do that. So, question. This methyl group is coming from the top, right? So what is the up position on this chair? Is it up equatorial or up axial? Equatorial. So we're going to write here on an up equatorial. And it's kind of subtle what's happening here. So we also have a hydrogen here. But when this methyl group shifts over, for like a brief second, what we have is we have a CH3 here and a hydrogen here. And then it kind of rotates down. So it's when this moves over, it starts up axial, and that's not an up axial carbon. And so when she shifts to her normal chair, it's going to go down to the up equatorial for that CH3. Do we follow that kind of like shift down of like we have a transition state where we have CH3 up and we have H like this, and it's just going to kind of rotate down and get to its normal chair. It has to do with this alignment of orbitals. So because you have to align the orbitals and this is going to be coming from up, then it needs to be up over here. Yeah. We're about to see. So where do we have a carbocation now? We've done a rearrangement. So this is a planar sp2 carbon. And is this a, what type of carbocation is this? She's a resonance stabilized carbocation. She is so much better than a primary, secondary, tertiary, or even a Lilic, because we can draw a resonance structure here. Oh wow, that's a rough chair. And here, our resonance structure has a positive charge on the oxygen, but she has a full octet on every atom. And that's big, huge. So this is an even better carbocation than a tertiary carbocation. And this is why we did this rearrangement, because if we just had our leaving group leave down here, then we would make a secondary carbocation, which is not the best, you know? And so by doing this rearrangement at the same time as our leaving group leaving, we get truly the best carbocation. Do you see why we do them at the same time rather than sequentially? Again, we would not ask you to predict that, but it's because we told you explicitly in the instructions that this happens. Yeah. It's planar now. So it's just kind of like, it's neither axial or equatorial. We don't have that anymore. She's FP2. So she's kind of in the middle. See, this would look ambiguous as equatorial and axial, and it's because it is. It's planar. This one?
Oh, it's still.
Because in resonance structures, they have to be the same. Yeah. So to get to our final product, all we need to do is our good friend Saul comes by. And we're done. So now I'm going to go pretty quickly because this section has already taken a long time. Down here, not y'all as a section, I mean this section of the notes. So down here, we're going to do the same thing of draw our anti-bonding orbital. And who does she align with? Who could do a little shift here? And to help us out, what do you notice is different between our starting materials and our products here? Yes, our 6-membered ring here turned into a 5-membered ring. So we know a carbon-carbon bond needs to shift. So what is something that is parallel to this? Dang dong. So we have this sigma CC that's immediately parallel, almost the kind of hyperconjugation little vibes. And what we're going to have happen is it just shifts over and we kick off our leaving group. Now, when we do that, it's going to be helpful to number. I'm going to do 1, 2, 3, 4, 5, 6. So we have the right ring that's unbothered. Then we have the down position, the up position. And this is 6, 1, 2, 3. 3 is still connected to 4 going down. But now we have 6 connected to 4, don't we? Because here, when we move this over, 6 is now the one it's connected to. 6 is connected to 4, 6 is not connected to 5. So I'm going to redraw this slightly to kind of show more of the like little dip. 4. So where is carbon 5? Who is carbon 5 still connected to? Sure, but what carbon is carbon 5 connected to? No, 6 just shifted away. 4. So on 4, we need to draw this carbon 5 here. And that 5 is going to have on it an OH and a CH3. And then where's the carbocation going to be? Who did we rob a bond from? No, 6 went from bonding to 5 to bonding to 4. She's good. Who did we rob it from? 5. 5 had a bond to 6, and now she does not. And again, what type of carbocation is this? A resonance stabilized carbocation. So we have a resonance structure. At this point, I'm not going to draw this crazy weird chair thing again. I'm just going to draw this. And then we can just have our good friend Saul finish it off. So these are hard. These are not the straightforward, these are not your grandma's carbocation rearrangements. These are like more complex. And again, we would not ask you to do this on like an exam situation unless we gave you explicitly a product that could help you piece together what happened. And I would still say this is probably beyond what we would ask on an exam. But I'm just used to help room, like y'all. I don't want to say y'all do terribly on this without some instruction. But like this is just a little bit further beyond the grasp of what's in y'all's ballpark now. And so hopefully doing it here together will make that question easier when you're doing your write-up. Yes, and then we have to go on. Because when you move over like this position is going to be the up, and the H that was over here is going to be down. So you have this up, H down, this up, H down. It's kind of weird when you're moving between it. But to be honest, if we give you the stoichiometry in the product, just be like, that happens. Yeah. Didn't have time for challenge problem 2, and I figured I added a lot this year. But we are moving on, moving and grooming to making alcohols leave. So the problem, alcohols, typically not a good leaving group. So let's start off with a half-baked solution to this. So our half-baked solution, dump it in a vat of acid. What could go wrong? So if we put it in really strong acid with hydrobromic acid or hydroiodic acid, and you have a tertiary alcohol, she can do an SN1 reaction where we protonate her, leaving group leaves, and then the bromine or the iodine can go and attack the carbocation. So it's just SN1. And then if we have a primary alcohol, we can do SN2, where we protonate it, it's a good leaving group now, and then the BR will do an SN2 attack. So, like, I mean, these aren't new reactions per se. We're just using it in a new context. Like they're not new mechanisms. But why is this a half-baked solution? Well, for one, what about me? Not meso, me, the secondary carbon. So what about me? Like that's going to be fair for SN1 and fair for SN2. So not ideal. The other thing is you're dumping it in a vat of acid. So if you have a complicated molecule and you're doing a synthesis, and you have something that's like sensitive or would react with acid, because you've run many reactions with acid now, this is not going to be helpful. So should you ever put this on a synthesis question? Probably not. Like that seems a little like sus. It's, I don't know. I guess you could have a lot of money and like waste reagent, but so this, again, it's more kind of conceptual, but this is not going to be your like go-to for a synthesis, something like that, or a line reaction. Yeah. Typically, no. Like hypothetically, sure, but this is not going to be our main Jane way to make alcohols leave. Let's meet our main Jane. So our main Jane is we turn them into better leaving groups and like legitimate other mechanisms. And like that is what we teach. So we have 3 reactions, new reactions here that make alcohols leave and that are a real solution. So we can tosylate it. And when we tosylate it, essentially what we're doing is we're having an attack the S, kick off the Cl, and then we have this structure, and then we deprotonate it, and now we have an OTS. And OTS is a tosyl group, and it's a really great leaving group. Now, one thing you should note is we started on a wedge, we ended on a wedge. So we retained our stereochemistry. So that means we didn't do an SN2 at this step. Do you buy that in the mechanism that there was no SN2 attack here? Okay. Now, the other ones that we could do are we could replace the OH with a Cl or a Br. And these do an SN2 reaction. And the first thing that you should think when you do an SN2 reaction is, wow, it's like I'm leading a cult. Okay, so again, the same kind of thing. First step, you attack, kick off the chlorine, and then you have protonated, and then you deprotonate it. And then the chlorine ion that you kicked off over here comes back and does a backside attack, kicks this off. We make SO2 gas, which is super stabilizing. And here we wind up with an inverted stereochemistry here from what we originally had because we had an SN2 step. PBR3 is really similar, and you have the BR come and do a backside attack, and you have inverted stereochemistry. So our main question with like, how do we determine which one of these we want to use is, do we want to retain the stereochemistry or do we want to invert it? So this is a variant of page 14 of the skill builders. I think I made it into a better question, but you know, I'm conceited. So let's start off with the easy mode where it's giving us something and we have to predict what happens. So SOCl2, our fake mechanism is we just replace it with a Cl. But the big question is, do we retain or invert the stereochemistry? Invert, because this is the one that has the mechanism where the chlorine does the backside attack. So we have an SN2 here, and then KCN. So we have a CN minus nucleophile. Now, is this going to do like an SN2? Well, I'm telling you it does. Yeah. So we are adding a CN there, and should it be on a wedge or a dash? Wedge, because we've inverted. So, ooh. A double inversion is a retention. Oh. A double inversion is a retention. Can you say it with me? A double inversion is a retention. Wow. Okay, so now let's look over here. So we start on a wedge and we end on a wedge, and we have to make an alcohol leave in the middle. So did we overall retain or invert? And so if we're doing retention, what do we have to do? Thank you. Thank you. So we know that we need to do something here that makes a leaving group on a dash. So what's your favorite reaction that does this? Sockle, sure, or PBR, live your truth. I'm going to do PBR because we just did Sockle right above it. Also, like in the past, students have been like, well, PBR is a type of beer, and beer is an alcohol. So, and then you go to a bromine and it's like, bruh, can you pass me the alcohol? It's a PBR. I don't know. I don't know. Isn't that how bruh speak? No? Okay, and then what nucleophile do we need to add to replace the BR with an N3? Yeah, we obviously need an N3, and then she's negative, so we just put an Na on there to kind of cover up that negative charge. Okay, so now the second one, overall, do we have inversion or retention? Inversion, right. So what does that mean that we need? How many SN2 steps do we have? That's what I should say. 1. And we know that that SN2 step is going to happen here because we're doing the SN2 product here. So how can we draw an intermediate here where we keep our leaving group on the wedge? What should we use? Tosyl, TSCl. I think we include pyridine for her. So we keep it on the wedge. It's an OTS. And then what nucleophile do we use to add an SH? So we definitely need an SH. What else? Our good friend Nash. You hurt his feelings. Oh my gosh. Yeah. Yeah. Pretty much. Yeah. Yeah. I think we just stumbled upon a wild synthesis strategy. So if we want to replace an alcohol and invert the stereochemistry, we do a single SN2. Whereas if we want to replace the alcohol and retain the stereochemistry, we need to do a double. I'm really loving these sound cues. I have a playlist that's just S17 sound cues. This is my first time doing it. Thank you. Thank you. And also I had the hidden box. We really made it a production. Organic chemistry as theater. Yeah. Like literally I had her and then I dragged her away. Oh. So again, this is something that this will choose whether or not you want to use Sockle or PBR versus tosyl chloride. If you want to do your double inversion and get an overall retention, you use PBR or Sockle. And then if you want to just get an overall inversion, use tosyl. Cool. Questions on this? I'm glad that worked. So the other thing here is challenge problem 4. So challenge problem 4 uses POCl3. Is that one of our reagents? No. And it gives an observation of like, well, if we did this with like a primary alcohol, we would get the substitution, just like our good friend Sockle. But something here weird happens. So what is the first step with all of these alcohols and the sulfur and phosphorus electrophiles? Like, what are the first arrows that you do? The O attacks it, and then what happens? Kick off the leaving group. Now it's going to be tempting to kick up the here, but this is not a carbonyl. So with sulfur and phosphorus, you'll just kick off the leaving group. Let's try that down here. So we have the OH attack, kick off a Cl. Okay, then for example, for this Sockle, our next step is what? Deprotonate. Okay, so here we have pyridine. We know that's good base. Boop, boop. Now, if we had gotten the replacement thing that we would expect with like Sockle, this is the point where we would attack from the back and replace. But instead we get an alkene. So what reaction did we do instead? Elimination. So let's try out an E2. Do we have a base? Yes, yes, we have a base. Okay, pyridine. Now, the first thing that you should think with E2 is, thank you. And it's an anti-periplanar orientation of what two things?
Leaving group and the hydrogen, beta hydrogen.
Great. So we have a leaving group, we have an alpha position, a beta position. And so our hydrogen that's going to be anti is the one that is down like this. And we could do it on either side, both work. For 5-membered rings, we don't care about you drawing the chairs. We can just be like, that's anti. So our pyridine comes along, deprotonates, pushes in, we kick it off. And just like that, we're done. Yes. Yes, and this is the thing where like, this is a question that should be pretty easy and quick. I've just seen students struggle with on the past because you're trying to be like, but in lecture, we learned this. And yes, this is not that. So that's why I said now and on separate. Okay. I hate to keep just plowing through it, but I wanted to make sure that we have some time for these longer problems at the end. So I'm going to do another hard pivot. Ethers, my least favorite functional group. So I've tried to make her just a little bit more interesting to me, but really this is my least favorite lecture the whole summer. So we really were trying to like, how can we make this interesting? Pokemon. That's what we're doing. So ethers, one thing that's helpful, that's like a me thing, that's not something that I've read in a textbook, is I think it's helpful to think about ethers in terms of how we classify the carbons on either side. So is this a primary, secondary, or tertiary carbon? Primary, it's only attached to one other carbon. Even though it looks kind of secondary, we don't count the oxygens. So I would call this a primary plus, and then what's on the other side? Primary, secondary, or tertiary? Secondary. So I would describe this as a primary, secondary ether. Okay, the next one, what's on the left? What's on the right? A tertiary, secondary ether. Third one's gonna be primary, tertiary, and then fourth one, secondary, secondary. So right now it's kind of like, great, more nomenclature, fun. But this I think is going to help us see what's going on in these reactions. So let's talk about how to build an ether, how to save a life. We have two options. The first option is the classic, the go-to, the Williamson ether synthesis. So when I say ether, you say Williamson, ether, ether. When I say Williamson, you say ether, Williamson, Williamson, ether, ether, Williamson, ether. Good. That is the one ether reaction that you're going to use a lot on like synthesis and line reactions. So if you take away nothing else from this section of the notes, take away this, the one that I made you like demon chant, like, we're excited to see you here, like the sororities in the South, you know? So the basic outline of Williamson ether, you start off with an alcohol, and this can be in any prime alcohol, primary, secondary, or tertiary. So I just call her any prime. Again, this is a me thing that just helps me organize it. So you deprotonate it. It's now an alkoxide after the first step. And then you introduce a primary alkyl halide to do an SN2. And when you do that, you wind up with an any prime plus primary ether. Now, why can you only do this with a primary alkyl halide? What type of reaction is this? What is the one factor that affects whether or not an SN2 happens? Sterics. So here, the reason why we can only do this with an any prime and a one prime is because you need a good electrophile for an SN2 reaction, because overall this is just an SN2. Fair enough? The other way that we can do it is SN1, and she doesn't have like a fancy name. So you start off with a tertiary alcohol, and then you can have an any prime alcohol. And what you do is you put it in acid. So it forms OH2 plus, the leaving group leaves. Then you have your carbocation that's tertiary. And then your other alcohol goes in and attacks. And then after deprotonation, you got your ether. So this is like a pretty standard plain Jane SN1 mechanism. Neither of these mechanisms are new. It's just we're using it to form an ether. And that's the thing that's new and kind of weird. So one thing I think that's helpful that I didn't bake into the notes this year, which I'm going to bake in next year, is just seeing where these wind up. So like, did this alcohol come from our any prime alcohol or our primary alkyl halide? Yeah, it has to be the alcohol, right? So we have this here. And then this was from our primary alkyl halide. So here. But here it's a little bit trickier. We have two alcohols. So which one did this O come from? Our any prime or our tertiary? Ooh, mixed results. Well, we know it's SN1. So we protonate this, and this leaves as water. So she is gone. So the O that's in the product is from our any prime over here. And then that means that this tertiary carbon is from the tertiary. So with this, like, for example, of 1, 2, 3, 4, which of these could we make really easily with a Williamson ether? 1 and 3. Why? Exactly. So if you need to make an ether where one side of it's primary, use Williamson ether. It's really direct and it will get you your product really easily. Now, which of these could you make with the ether acid in synthesis, the SN1? We can make 2 or 3 because for an SN1, you need the tertiary. So this is why I think this nomenclature and this way of thinking about ethers is helpful, because you know the reaction's either going to be SN1 or SN2. And if you have a primary somewhere, it's probably going to be the SN2. And if you have a tertiary somewhere, it's probably going to be the SN1. But this one has both, so you could do either. There's one catch. Secondary. Secondary good for SN2? Is it good for SN1? Tough. Oh, wow. So that's just one thing to watch out for. If you have a secondary, she's complicated and she's messy. So she's probably not one that we're gonna give you on a test. Good. We're gonna get there. Pretty much. And it's why it's a little bit more Wild West. You just like add asset. One note, you can make cyclic ethers if your nucleophile and your electrophile are on the same molecule, which y'all have seen before with like hemiacetals, acetals. The other thing I want you to be watchful for, you will learn 2 other ways to make ethers. So be on the lookout. How am I going to make the other ethers? You should ask that just over and over. Where's the ether? I need 2 more. Where are they? Just, yeah, raise your hand and be like, is this the other way of making ethers? And then Tim will be like, the other way? Yeah, I mean, we're just making ether. But like, iconically, this is a like scavenger hunt. Find the 2 other ways to make the ethers that we don't put in the ether part of the lectures. Ooh. Oh, we'll see. I'll make sure you know. I'll make sure you know. Okay, now step 2, how to destroy. So we have 2 options. One's SN2, one's SN1. To be very honest, I don't really want to talk about it very much because both of these strategies are throw it in a vat of acid. So is this going to be a practical thing to do on a synthesis or a line reaction? Not really. This is more for us to kind of think through conceptually like, okay, well, if you have a primary over here, then that can do an SN2 rather well. So we can do that. If we have a tertiary over here, oh, SN1. Oh, like, sure, it's a thing that's like required to teach, but I think these reactions are kind of boring and they're not tested very much. So I'm gonna like keep on going if that's okay. And again, the warning, secondary is weird and wonky because it's not good for SN1 or SN2. There's a skill builder page that kind of explores that. So have fun. Any questions about my least favorite functional group? She's boring. She's not reactive. She's not very interesting. I don't think she has a rich interior life, you know? She's not concerned with growth. And as a friend, I'm really frustrated to hear that. But now let's go on from the least favorite functional group to the most dramatic functional group. So an epoxide. She's about to explode. I love her. She is strange. She is in ether. She's the only interesting ether. A 3-member cyclic ether that is ready to erupt. Her street name, Oxirane. Wild. This feels like one of those like made up words of like, what are we doing? I also like just think she's kind of cool. So this is the cool ether that looks down on all the other ethers. So here we are. So let's talk about how we make ethers. Not ethers. How we make epoxides. Thank you. So we have yet another functional group. They don't stop time. So we start off with something called a halohydrin. So can you say it with me? A halohydrin. 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 So it's when we have an alcohol and an alkyl halide that are neighbors. Cool. So what happens is we add base, NaOH. You could technically probably do NaH. Minus here, just as like a backside SN2 attack. So casual. Now, there's one more way you're going to learn how to make an epoxide in lecture 8. And she's my favorite reaction this whole class. So be on the lookout. She's coming and she's much more interesting. Go ahead.
This reaction was really like
That's a good question. My immediate reaction is like, if you heat things up enough, shit goes down. Like, if you add base, it's deprotonated, and you keep hitting it like with more and more heat, the molecules are just going to be bumping around, and they're just going to do this. Yeah. but that's not a great answer, so. Cool. So making synthesis is pretty straightforward, one-step mechanism. What the real fun comes is breaking the epoxide. And so I have a meme. So me, the boys, a cold one. I'm cracking open a cold one with the boys. We love a homegrown. So, epoxide opening, we said that she's very reactive, but the question that we have is, does our nucleophile attack here, or does it attack here? And this is only really a concern when we have sides that are not equal. So here we have one side where what's the carbon here, primary, secondary, tertiary? Tertiary, and then the bottom one, secondary. So we have a more substituted side and less substituted side. The way that we control which side we attack is whether or not we do it in acid or base. So acid will have the nucleophile add to the more substituted side. So here my nucleophiles are in red for the acid, and they're going to be adding here to the more substituted carbon. Whereas here in base, my nucleophiles are here in blue, and they are being added to the less substituted side. Now, when I say acid, you say more. Acid, acid. When I say base, you say less. I didn't say base. I say base, you say less. Base, base, acid, acid, base, acid, acid, base, base, acid, acid, base, base. So this should be like one of the immediate things that you think about. When you have an epoxide, you need to know which side you're opening from and which conditions. So let's talk about why. So when you're in acid, you protonate this epoxide, and already you have like a partial negative, partial positive, just from electronegativities, right? When you add a positive charge on this oxygen, it makes it even more electronegative. And so it's going to make a bigger partial positive here and here. Now, which of those partial positive charges is more stable? The one on the tertiary carbon or the one on the secondary carbon? Tertiary. So it's kind of weird, but it's kind of like in this liminal space between being just like a partial positive and a carbocation. And so because this is the more stable, like almost carbocation, the nucleophile is going to attack here when it's in acid. It's because the more substituted side better stabilizes this partial positive charge. In base, it's truly just, it attacks the less substituted side because it's faster. There's not like a deeper reason. Questions about her and why she does that? Cool. So let's talk about what we can add to an epoxide. Well, we can add an alcohol, and what do we get? What did I tell you to look out for? Wow. Wow. Okay, that was less of a reveal than I had hoped. But yes, this is one of our other ways of making an ether. We can make it from an epoxide where an alcohol attacks it. Now, here, H3O plus, our nucleophile is actually going to be water. And so what we get is an OH here, and we have neighbor OHs in the same vicinity. They're a vicinal diol, also called a glycol. So importantly, here you have an ether and an alcohol. You have kind of two interesting things happening. But remember, ethers aren't that reactive. So you only have really one reactive group. Yeah. We'll get to the base, so that's okay. So here, when you have a vicinal diol, you have two pretty reactive functional groups that are neighbors. And that's an important thing that's going to come back, okay? So two reactive neighbors together, vicinal diol. Now, when we are in base, if we do an alcohol in base, then we're going to add to the less substituted side. So our OR gets added here. And again, we have an ether and an alcohol. And then another base that you might not think about is a Grignard. So Grignards, you're used to having her attack a carbonyl, but she's basic conditions. And so she's just going to attack the less substituted side. And the mechanism is exactly what you would expect. It's this, then you have an O minus, and then you do your acid workup. And you neutralize it. Now, one big question here, so we see the regiochemistry, like it adds to the less substituted side because we're in base. But why, for all of the things that we've added, why are they all on dashes? Kind of. Yes, we'll go with that, inversion of stereochemistry. I get this question, and so I made this little diagram last night that I think is helpful. So if your epoxide's coming up, then your antibonding orbitals are going down. They're beneath the ring. And so no matter which side you're attacking, your nucleophile is going to be attacking from below the ring. And that's why when we add our nucleophile, it's always add on a dash here. If instead we had an epoxide where our epoxide was beneath the ring, then would our nucleophile add and be on a wedge or a dash? A wedge, because it would have to come from on top of the ring. Kind of makes sense. Also, if you don't have something really strained, or if you don't have like a stereo center, you don't have to think about all the dashes. So there will be a lot of epoxides that are a lot easier. But this is how to crack open an epoxide. Check. That's a good question. We're gonna say no. Hypothetically, yes, but we're gonna say no. I think it's just right now a little bit beyond y'all's pay grade. So the polymerization reaction, I think it might actually involve some radicals. I don't know about her yet. But I would just say for right now, don't worry about it. I know that didn't answer your question, but. No, like if you just do this, like it needs to be to the correct carbon, but no, you don't need to show bottom or top. In the piece set, when I was asking about that, it was really just when you like conceptualize it. Yeah. So with that, let's do a synthesis. Challenge problem 10. Now this is a 10 stepper. And we're gonna spend a good 20 minutes on this. Okay. Now, what is the first step we should do whenever we get a new synthesis? Functional group analysis. Go through the starting materials in the product, circle any functional groups, label them. And don't look up here because I'm going to be doing it too. How'd you do? Did you catch that this was a halohydrogen or words, halohydrogen, and not just an alcohol and a bromine? No,
Yeah, this is the
sure. But yeah, I guess. Right now, you just don't know any reactions from there. But I feel you. So halohydrogen, the next step once we do our functional group analysis is what? Mapping, and then there's another one. We're missing one step before that. That's with brainstorm. Like I know it's kind of like, don't go into an essay without pre-writing. Like we've labeled the functional groups, but the thing is, y'all are new to this. And so when you see alcohol, you don't immediately have all the reactions that alcohols can do in your head. So we have to like brainstorm them together and write them out. So what are things that we can do with alcohols? What functional groups can we turn them into? Yeah, we could like oxidize and make ketones or in this case, we couldn't make a ketone, but we could make an aldehyde. And we can make carboxylic acid. What else can we do with her? Alcohol reaction. Almost like we had a section today, all the alcohols. Leaving group. So we can make it a Br, a Cl, or an OTS. And then last one is ethers. That's boring. Okay, halohydrin. What is the one thing you know to do with a halohydrin? An epoxide. Yeah. So why don't we go ahead, since we know that that's the only thing we can do, let's go ahead and make the epoxide. And what reagents do we use? NaOH. Okay. So we have an epoxide, and then let's look at the products. So alkanes, how can we make alkenes? E2 or E1. So we know that we need something that has like a leaving group, and we can either have our leaving group here, or we can do it with our leaving group on the other side. Like a leaving group here. Does that make sense? As like, if we have to do an E2, we need a leaving group in one of those places. Okay. Now, ether. What's the thing that you should think when you hear ether? Williamson ether. Okay. So we should be thinking like Williamson ether. And Williamson ether is for what kind of primes? Blank prime and blank prime. Any prime plus 1 prime, because we're doing SN2. So which side is our 1 prime? Is this our 1 prime, or is this top one our 1 prime? The top. So we're gonna need an ethyl bromine at some point. And then we're gonna need like OH, like here. Okay. Interesting. Very interesting. So we've done some good brainstorming. Now let's try to map our starting materials onto our products. So what are some distinct features that you see in both of them that are common? Well, yeah, phenyl group. Phenyl group. What else? Yeah, the dimethyl. The geminal dimethyl. Gemini, twins on the same carbon. So we know those are probably the same. So let me extend this out, and I'm gonna call this girl green star. I'm gonna call this girl orange star. So orange star is gonna be here, and then green star is going to be here. So the central like core difficulty that we're gonna have in this whole thing is we need to create a double bond between green star and orange star that are in different molecules. So what we need to do to bring these together is we need to say one of them is a nucleophile, one's an electrophile. So we need to try to turn one into nucleophile, one into electrophile. Now, we know this one goes into an epoxide. Is epoxide nucleophile or electrophile? Electrophile. We're opening the epoxide. It's what's attacked. So maybe let's try making this the electrophile. And so our green star is here. So what if we just made our orange star into some sort of nucleophile that could attack here on this green star? Well, so green star, we're attacking on the more or less substituted side. So are we going to be an acid or base? Base. Okay, so we need a base nucleophile. So how can we turn an alcohol into a nucleophile? Our aldehydes are carboxylic acids nucleophiles? No, they're all electrophiles. Ethers don't really react very much unless you dump them in a vat of acid. And then bromine, chlorine, tosylate. Are any of these nucleophiles? Are any of these nucleophiles? Tosylate? Is that a nucleophile? Bromine or chlorine? None of these are. So what do? Boom. If we take our alcohol, we turn into a bromine, which is a reaction that we learned today is something that we could do. Bromines we can turn into Grignards. And suddenly, Seymour, we have this orange star is a nucleophile. And is it a basic nucleophile? Yes. Oh, ding dong. Okay. Our reagents to get there. How do we turn the alcohol into a bromine? EBR3. Bruh. Alcohol, right? Am I right? Okay, and how we turn a bromine into a Grignard? Good. And then we don't need acid workup. It's all just one step. Okay, so let's try it. Let's try doing this together. So we have this epoxide, and we are going to do 1 pH MgBr 2 H plus. Let's see what we get. So we are connecting again the orange star and the green star. And what we are going to have is our green star down here. We've now made a bond to the orange star up here. And then we have our phenyl ring. Okay, we've made the bond. So now we need to make the ether, we need to make the alkane. Oh no. Oh no. To make the alkane, we need a leaving group. Like on either this carbon or this carbon, one of them has to have a leaving group. That's an alkane. We don't know how to turn an alkane into a leaving group. So welcome to our first failed attempt. Failed attempt. Number 1. And so I'm going to turn her gray because she died. That's okay. We needed to work through it. We needed to think through this in order to get to where we need to go. So notably here, I think the key thing has to do with this epoxide, right? Like we need this epoxide to open and we have functional groups on both of these carbons that we can work with. So let's go to our epoxide opening. Well, here we see an alcohol plus an R group. That explains our only one functional group. Which of these will give us 2 functional groups that are pretty reactive? Well, it gives us an ether and an alcohol. So you're thinking here, let's try it. So let's try. We have this, and then we're probably going to use ethanol, right? Because that's the ether that we have in the product. ETOH, H plus, 1 step. So if we do that, then we attack the more substituted side. So our OET is here. And then we have an OH. Okay. So now this is where our green star is. And the green star, what we still have to connect everything, right? So how can we connect green star to orange star? Yeah, sure. Yeah, what made you think we might need to oxidize it? Yeah. Which is what type in a reaction? What is it function as? An aldehyde. A nucleophile or electrophile? Exactly. So again, whenever we need to make a bond, we need to think about what's the nucleophile, what's the electrophile. We made this into a nucleophile, so we have to make this into an electrophile. Okay. So how do we oxidize the alcohol? We gave her a round of applause. What's her name? For the people in the back. I need more volume. Thank you. Chromium, our OG. She's coming through every time we need her. And what sidekick is she using today? Iridine, because we want to stop at the aldehyde. So we have the aldehyde here. Now, shall we try attempt number 2 of making the bond? So we do 1, our Grignard that we made earlier. 2, H plus. So our product from that is, we still have our ether here. Remember, she doesn't react very much. And then we have an OH here. And then we've added our phenyl group. And if I do my little stars, green, 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 and orange, orange. So, do we have a position here where we could turn this into an alkene? We have a functional group here. That's the important part. Is she a good leaving group? No. But do we know a way to make an alkene from an alcohol? We blank it. Honk it. So we have a secondary alcohol. If we use concentrated H2SO4, we are doing an E1 reaction and we eliminate and we can do it straight away. The other way that you could do it here is you could do like PBr3 and then you have the bromine and then you add in like OET. Now question. Why did you form a bond here rather than here? Really need volume. There's no beta hydrogen. So there's only one option for the alkene that we can make, one side, because this has carbon, carbon, oxygen, like there's no beta hydrogen there. Good. Another way that we could have done it, and the way I did it in the section before this, is we made this into a glycol, and then we oxidized it, and this alcohol cannot be oxidized. Why? What did I just say? Thank you. Because there's no hydrogen here to take it, so it cannot be oxidized. So then you can oxidize this and make it the electrophile. Do your Williamson ether here, make your ether, and then you're gonna have the Grignard attack this, and then do your elimination. That also works. So there are several routes that work, but this was not like a straightforward, easy path. Like this is something that you have to work through and struggle with. This is something that like is an active thinking, like almost kind of creative process of like, how do I think through all of these tools that I have and use it to accomplish a specific chemical goal? But do you see how at every step of this, at every step of this process, we had things that we were trying to do. Like we had action items, functional groups, brainstorm, map things onto each other, identify a bond that needs to be made, make a nucleophile electrophile. These are the things that guide us. And again, if you are not doing this on a synthesis, or if you are just staring at it and not kind of using your paper to help you think, I think it's going to hinder you. Go ahead. Well, I mean, you're reacting to separately. So, like step 1, and then that we turn in 2, 3. Then here, these are separate, 4, 5. Combine them 6, 7. We did an 8. Unless I missed something. But again, the other routes I did had a couple more reactions, but they were still 10 or fewer. And also, if you take more steps and get to the right thing and have it fully like correct, then we'll give you points, like we said, best things. Now, extra challenge problems. Who wants a paper copy? Give some and pass some. So, what we need to do now is another hard pivot. We love to see a hard pivot. It's our favorite part of section, right? So what we are going to do now is we are going to do SN1, SN2, E1, E2, our GFP system. So for each of these, what I want you to do is write SN2, E2, SN1, E1, and I want you to grade them and do the GFP system, see which one's going to be best. Now, some of these are a little dark-sided. They have some tricks up their sleeves. You can already tell we have a ring. So what are we probably going to need to draw? A chair. And then I would just, that's the hint I'll give you for now. I'll let you work. I'll let you cook. Y'all, I don't know. I don't know if it's because y'all are a captive audience or because you actually think I'm funny, but I'm so flattered by the laughs. Probably the captive audience. The fastest I've been to that for that symptoms problem again in like 5 years. Y'all are quick. Anyone else need the attendance sheet? You need the attendance sheet or two? Need to find more sound cues because I really enjoy them. There's one in lecture 10 that I'm really proud of. What? Well, I did it last year and it was truly, I was like, wow, I'm becoming unhinged. And now I've just baked it in. I'm doing it every year. I'm doing it every time I talk about this reaction. You know, it's a works. It's truly a Spotify playlist. I queue up the time code before. Like, so in my last section, I played Chantel's Impossible when there was no beta hydrogen. And we love to see it. I told that to Tori and she just like lost her mind. Like she's like, what are you doing? I said, I'm not supervised. Oh. I'm gonna give you like 30 more seconds. I know you've not had time to attempt everything, but maybe you'll have gotten through one or two, and then we can talk about the rest together. Cheryl. No, they're not Cheryl, they're Andra. Andra, I have you on my roster for 8 a.m. If you sometimes come to my 8 a.m., or are you always in the time? Okay, work. Andra. Then we have, I was gonna call you Alex, but you're Tate. You're one of the two Tates, and the other Tate isn't here. Okay. And then some, and then Jackie. Also, it is Toledo, it's not Tower, right? Work. Then you have John. Then there's someone next to John. Yeah, there's John. Oh. And- Andra, I promise I will get it first time next time. If not, I'll light myself on fire. What? So when he did the E2 on a ring, I forgot that he teaches that in the lecture. I was like, I'm really on the game. Oh. And then when I did some of the MO theory before he did it the next day, we love to see it. I'm really just trying to like usurp power. Okay, let's rank this next one. So SN2, are we good, fair, or poor? Why? Because we are tertiary. E2, are we good, fair, or poor? Why? We have an acid as our base, yes. SN1E1, good, fair, or poor? Good, why? Tertiary carbocation. So we are going to form this carbocation after our leaving group leaves. And then what happens when we conk it? We have the choice between SN1, E1, and we have concentrated H2SO4. We are only going to get E1 because we don't have a nucleophile. Concentrated H2SO4, it can in no way, shape, or form be a nucleophile. So we have some options for double bonds. Some of you might have done this. Some of you might have done this. Left, right. Who is correct? Why? Zaitsev's rule. Thank you. That the more substituted alkene is more stable. Moving right along. We have this SN2, good, fair, poor. Fair. E2, good, fair, poor. Good, because why? Strong base. And then we forgot to say secondary here. And then for SN1, E1, good, fair, poor. Fair. So what wins? E2. Now we're doing E2 on a ring. So we have to draw our chair out. And do we want to put our leaving group axial or equatorial? Axial. Because that's the only way that we can get our E2. Wow. Thank you. Wow. Okay. And then this terbutyl, or this non-terbutyl, this is an isopropyl. So she's going to be down right here. So let's look at our beta hydrogens. We have, this is a beta position, this is a beta position. We draw out our hydrogens. How many antiperiplanar beta hydrogens do we have? Only one. So we are going to form the alkene that is here. Now, even though it looks like if we formed an alkene here, it would be more substituted, so more stable. This hydrogen is never going to be antiperiplanar up here. So we just can't form the alkene on that side. I'm going to keep plowing just to get through these because we're at time, but I want to like say these real quick. This one here, SN2, are we good, fair, or poor? Good. Nucleophile vibe check. It's not that it's bulky, it's that it's an alcohol, not an alkoxide, so it's neutral. And so alcohols, 4 nucleophiles. E2, base strength, good, fair, poor. 4, SN1E1, good, fair, poor. 4, oh. Well, let's see. If we just did our leaving group leave, what kind of carbocation is this? Resonance stabilized. So this is better than the tertiary. I know. This is us being sneaky. This is us being real sneaky. That has a positive charge. And now, once we have this, what can happen? Like we have a carbonyl. A protonated carbon. Kind of like our first step of like acetal formation. So we have MEO carbon. We still have our 2 hydrogens here. And then we've added OET. So we actually made an acetal. Wow. And this was a good acid one. Cool. Last one here, really quick. NaOH base. What is, oh, I should do the SN2, all the things. SN2, good, fair, or poor for our leaving group. Good, because we're primary. Base strength, is it good, fair, or poor? Good. S1E1, are we good, fair, or poor candidate? Poor. So what's gonna happen? SN2. So what do you think, like, how would you go about trying to write the product? Would you do like we're substituting? That is the one to expect, but we have something going on over here. So in acid, we are going to deprotonate her and we have S minus. Then we have a nucleophile and the electrophile in the same molecule. And so we're going to make a 1, 2, 3, 4, 5-membered ring with a sulfur. So we're doing SN2 here, but intramolecular. So do you see how we've taken the kind of basic skills that we worked on last lecture and just kind of elevated them? Like we've made them sophisticated. We're like the Michelin star restaurant of substitution elimination questions now. These are tricks that should feel like tricks and unfair now. And by the time you get to the exam and like have done more practice exams and done more problem set things, these are tricks that you should know to expect. Okay? Sorry I went a little bit over. Thank you all for coming to section, and I hope you have a really great weekend, okay? Remember, be on the lookout for the sign up for meetings email and fill out the survey. Thank you. Oh, girl. Were you here when I shared my screen for the, no, you weren't.